Good morning, students. In our last class, that is in physics, chapter 15, volume 2, we were discussing some of the important terms to explain the wave and its wave motion. That is, the first quantity I introduced is nothing but wavelength. For example, used to represent the wave in this form. The wave is propagating along the x-axis, where x-axis denotes the direction of propagation, and y-axis, that is positive and negative, denotes the displacement. What it denotes? The displacement of the particle along the y-axis, that is upward as well as downward. This is a transverse wave. What it is? A transverse wave. This maximum displacement, we call it as what? Means we call it as crest. That is A, B I would have denoted, and this A, C I would have denoted, and this B and D I would have denoted as trough. This is the maximum displacement in the negative axis, that is in the positive axis. Then what is a wavelength? Means that is from A to C or B to D, or from this point O to P, we call it as wavelength. What we call it as? Wavelength. This is the first quantity I introduced. The second quantity I brought forward in our last class is nothing but time period. What is time period? Means it is denoted by capital T. What it is denoted by? Capital T. What is time period is defined as? Means time taken to travel a distance of one wavelength. This is lambda. We call it as lambda. To reach from A to C, what is the time taken? We call it as time period. Or to reach from O to P, what is the time taken? We call it as time period. Or from B to D, the time taken, we call it as what it is? Time period. And the third quantity I brought forward is nothing but frequency. That is denoted by the symbol nu. Frequency is nothing but number of waves. This is called as one wave. From O to P or A to C or B to D is called as one wave. Time taken to, that is number of waves per second. How many waves are passing or produced per second, we call it as frequency. What we call it as? Frequency. Number of waves produced per second, we call it as frequency, or it is nothing but reciprocal of time period. What is reciprocal of time period? After this, we went on to discuss about the next quantity, that is called as amplitude. This amplitude, this maximum value, we call it as what? Means we call it as amplitude. I would have denoted it as A. What I have denoted it as? A. Amplitude is denoted by A. And after this, I introduced the next thing is nothing but displacement. Here, displacement of the particle takes place along the y-axis, but the wave is propagating along in which axis? X-axis. That is, it is moving in x-axis, but the displacements are taking place in the y-axis. Therefore, y is a function of x and t, that is written as a sine kx minus omega t plus phi. This is the expression for displacement for the wave moving along in which axis? Positive axis. Positive x-axis. Suppose it is moving in a negative axis. That is, it is moving in positive. If it is, this is positive. If it is moving in negative direction, then it is given by a sine kx plus omega t plus phi. This is the displacement equation for a propagation in x-axis positive, and this is the displacement equation for propagating in the negative x-axis. This is what we have discussed in our last class, and I would have written it as a combination of sine and cos function. Just have a recap of it. And then coming to the next quantity I brought forward is nothing but, that is wave number. Otherwise it is called as angular wave number. Angular wave number is denoted by the symbol k, and its value is given by 2 pi by lambda. This derivation I would have shown you, that is only for the knowledge purpose. But this expression is very important. K is equals to 2 pi by lambda. And then this is with respect to the wavelength. To represent the wavelength, we have introduced a number called as angular wave number. And coming to the frequency, already we saw one frequency. This is another frequency, that is called as angular frequency. That is denoted by omega. This omega is called as angular frequency. That is given by 2 pi by t. Otherwise, omega is equals to 2 pi nu. These are the two formulas available for angular frequency. And the last quantity I brought forward is nothing but phase. Otherwise, phase angle. That is denoted by phi. What it is denoted by phi. I would have depicted some figures. Just have a recap of it. Two waves are starting in this point. See, these two waves are similar. Then both of them are starting at the same point. That means the particles are vibrating at the same point. Then I can say this is in phase. The two waves are in phase. Then what is the angle between these two? Means it is nothing but 0. Next, This is the two waves. This is A and this is B. This is A and this is B. Now they are moving in, and see here, this is starting in positive and this is starting in negative, exactly opposite. And this is called as out of phase. Out of phase means what is the phase angle? 180 degree. That means exactly opposite to it. Suppose this is starting in this fashion and this is starting in this fashion. Therefore, both of them are starting, but it starts from minimum to maximum. This is maximum to minimum. Then there is some phase. That phase is not equal to 0 and that phase is not equal to 180 degree. That means it lies from 0 to 180 degree. This is all about phases. What is about the phases? What is the phase means or phase difference means? It is the change in the phase with respect to the water, with respect to the displacement, with respect to the displacement. It's called as what? Phase angle. What it is called as? Phase angle. Up to here we have discussed in our last class, in our today's class, and then I went on to obtain the relation between omega and k. Omega by k is given by v, and another relation between the velocity, frequency and wavelength I would have got it as lambda into nu. These two derivation I would have derived. I have a glance of this. All this I have discussed under the volume 2 of your chapter 15. Now today's class, let us move on to the volume 3. That is nothing but in volume 3 we are going to see one of the important thing. What is the important thing we are going to discuss under volume 3 is nothing but we are going to speak about the velocity. What we are going to speak about the velocity of a mechanical wave. Our entire chapter deals with the mechanical waves. Now as I said, here the wave is produced. This wave, at what speed it is moving in x-axis, that speed only we are going to determine now. That is velocity of a mechanical wave. This velocity mainly depends upon the two parameters I said in the beginning itself. The first thing is nothing but it depends upon the elasticity of the medium. This one I want you to keep it very clear in your mind. Very important note. Velocity depends upon the elasticity of the medium. Next it is nothing but inertia of the medium. These are the two things it depends upon. Velocity of a mechanical wave mainly depends upon the two parameters. The first parameter I call it as elasticity and second parameter I call it as inertia. And here mechanical wave series of how many types? There are two types. Therefore, we are going to discuss about the velocity, otherwise speed of a traveling wave. Traveling, another name I gave is nothing but transverse wave. We are going to discuss. That is for crust and trough. This is crust and this is trough. For this wave we are going to find out the speed. What we are going to find out the speed, that is nothing but velocity. Next we are going to find out the velocity or speed of a progressive, otherwise it is nothing but longitudinal wave. This is a wind column. Air is divided in the form of segments. This is called as rarefaction, and this is called as compression, rarefaction, compression, rarefaction, compression. This is in terms of what? Longitudinal you can see compression and rarefaction. In transverse you can see the crust and trough. We are going to find out the speed. Here the displacement is in the direction of the wave, and here this is the displacement and this is the propagation. They are perpendicular. For this too you are going to find out the velocity or speed of the waves for a transverse wave as well as for a longitudinal wave. First we can go for the transverse wave, and after finishing that we can go to the longitudinal wave. Today's class we are going to see a very important topic, that is velocity of a mechanical wave. This velocity of a wave depends mainly upon two things. One is called as elasticity and second one is called as inertia. These are the two parameters it depends upon. Very important note, keep a note of it. And then mechanical waves has been classified into two types. One is called as transverse, another is called as longitudinal. Another name for transverse is traveling, another name for longitudinal it is nothing but progressive. In transverse wave there is a formation of crust and trough. In the longitudinal wave there is a formation of compression and rarefaction. These two, at what speed they are propagating, that is what we are going to obtain an expression for the velocity or speed of a mechanical wave. That will be our today's class. Now coming back to the thing, the first derivation I'm going to put forward is nothing but speed of a traveling wave. Speed of a traveling wave, otherwise another name is nothing but what? Transverse wave. This is what we are going to see now. Now see here, let us consider a wave. This is x-axis and this is your y-axis, positive and negative, where x-axis indicates the direction of propagation. What it indicates? The direction of propagation. That means the wave is moving along in which axis? X-axis. That is direction of propagation. Let me denote the wave. This is the wave. This is the wave I have denoted with an initial point. I am considering a point on it, that is nothing but A. This wave is at time t is equals to 0. This wave is at time t is equals to 0. This point is lying at this point on the x-axis. Okay. As time changes, then what happens? When you just make a move of it, this wave will start to move. Am I right or not? With respect to time. Then this wave, which I have denoted in red color at time t is equals 0, will start to get displaced. For example, it has moved to this point. Dotted line I am indicating after some time. Therefore, it gets shifted to this point A dash. Once again I am repeating clearly, understand. At time t is equals to 0, red color indicates the wave. That is at point 0. This is at point 0. If you just make a swing of it, then time will start to count. At time t is not equal to 0. This is at time t is equal to, for some small time delta t. The point A has moved from A to A dash. Then it has undergone a small displacement along which axis? Along the x-axis. That means from this point it got shifted to this point. That means it has undergone displacement. I have denoted it as delta x with respect to small time delta t. For some small time, this point A gets shifted to A dash. Therefore, from this I can say that here the displacement should remain constant. Here the displacement was maximum. For example, small a. Here also it should be same. Therefore, this is the point I am bringing forward. You know that expression for the displacement. Therefore, displacement y is x comma t is equals to a sine kx minus omega t. This is for what? For positive x-axis. The wave is moving along in which axis? Positive x-axis. Here see, I want to have a constant amplitude. What I have to have? A constant amplitude. For constant amplitude at any point, to any two given points. This is the two given points I have chosen. If you measure at the 2 points, the amplitude remains constant. That is nothing but A. For constant amplitude at any two given points, this is consecutive points. Consecutive means immediately, if I measure at this point, immediately next where it happens, at that point I have to measure. This is very, very important. At any two given consecutive points, then what is the case means? For constant amplitude, this is I am calling it as equation 1. For constant amplitude at any two given consecutive points, equation 1 should have kx minus omega t should be constant. Only if this case is satisfied, we can observe a constant amplitude. Because of this case only. If this is changing, then you will not get a constant amplitude. Once again I am repeating, understand clearly. This is the expression for the displacement for propagating along the positive x-axis. Here the wave is moving along the positive x-axis. For time t is equal to 0, I have denoted as red. After some time delta t, that red color would have been shifted to this blue color, that is from A to A dash, undergoing a small displacement. And then what is the amplitude it had? Same amplitude. Therefore, for constant amplitude at any two consecutive points, consecutive means again when I will get the same hump, that is at any two consecutive points, equation 1 should have kx minus omega t. This value should be always a constant. Only then you will have a constant amplitude. What you will have? A constant amplitude. See the figure. From figure I can say that x is changing with respect to time. Therefore, from figure x and t changes. What it does changes. Then equation 2 differentiating. What I am doing equation 2? I'm going to do equation 2 what? Differentiation. That is nothing but either you can use d or you can use the delta. I'm going to do here. K is a constant, it is a wave number. X is changing, delta x minus omega is constant, t is changing with respect to, that is delta t. Constant, differentiation of a constant is 0. Keep your mind of this, differentiation of constant is always 0. What it is always 0. K delta x minus omega t into delta t is equals to 0. This minus omega delta t, shall I send it to other side? Therefore, why k is constant means because k is equals to 2 pi by lambda. Wavelength remains constant. And wave number is also constant. Therefore, I can write it as k delta x is equals to omega delta t. Minus, if it comes to this side, it becomes plus. Then I can write sending k to that side. Then delta x is equals to omega by k into delta t. Sending omega t to delta t towards this side. Then delta x by delta t is equals to omega by k. Let me call it as equation 3. What I am calling it as equation 3. We know that delta x by delta t, displacement by time taken. This is displacement along which axis? X axis. Displacement along x axis, delta x, and with respect to time. Displacement with respect to time, we call it as velocity, where v stands for what? Velocity. Then v, substitute in 3, where I am substituting it in 3. Then v is equals to omega by k. This is the expression for velocity. Velocity in terms of omega and k. No sir, we know that omega is equals to 2 pi nu and k is equals to 2 pi by lambda. We will substitute in above. Then what happens here? If I substitute in above the equation v, place of omega I have to substitute 2 pi nu, and in the place of k I have to substitute 2 pi by lambda. 2 pi gets cancelled. Denominator of denominator goes to numerator. Then it is lambda into nu. This is the expression, and this is the, already in the last volume I would have derived this too by a simple method. This is with respect to a transverse wave or with respect to a traveling wave. Once again I am repeating, listen carefully. Speed of a traveling wave or a transverse wave. Let us consider initially at time t is equal 0. This is the wave. After some time delta t, this a would have moved to a point a dash. For some small time delta t. Therefore a has got shifted to a dash and undergoing a small displacement along the x-axis. Delta x is the displacement and delta t is the time interval. Then the expression for, we know that displacement along the positive x-axis is, this is the expression for constant amplitude. If you see at this 2 point a and a dash, the amplitude remains constant. When that amplitude remains constant means at consecutive points, it should have kx minus omega t is equals to constant in equation 1. If this is constant, then kx is changing with respect to time. As time changes, x also changes. From figure x and t are changing. Then equation 2 differentiating. Then what happens? K into delta x minus omega into delta t is equal to 0. On differentiation, I will get it as delta x by delta t is equals to omega by k. Where displacement by time taken, we call it as velocity or speed. Then v is equals to omega by k. This is for velocity in terms of omega and k. We know that omega is equals to 2 pi nu and k is equals to 2 pi by lambda. Substitute in above, I get it as v is equals to lambda into nu. This is the expression for velocity in terms of omega and k. This is in terms of lambda and nu. Is that clear? Let's see speed of a transverse wave on a stretched string. Very important for 3 marks this derivation. Just pay a note of it. Let us consider a string. If you take a string, let us consider in your terrace you are having a string that is used to soak the dress. If the string is very tight, then you are able to put the cloth very stiff, it stands on that. If the string is very loose, then if you put the clothes, that will touch the floor. Am I right or not? Therefore, I want the string to be very tight. When the string is very tight, then there is a tension in the string. When you pull that, it will start to vibrate. That type of string I need there. That means there should be a tension in the string. Is that clear? Let me consider this is a string along x-axis and this is y-axis. When you plug that, it starts to vibrate. This is a form of vibration. This is nothing but a transverse wave. What it is? A transverse wave on a stretched wave. At what speed it is moving? Now I am not going to derive as I did in the previous derivation, that is analytical method. I am not going to deal with that. In your second unit of your physics, units and measurement, you people would have studied about dimensional analysis. Using that method, we are going to derive the expression speed of a transverse wave on a stretched string. Using what method I am going to use? Using dimensional analysis. Using dimensional analysis method we can do. Just now I said that speed, in the previous thing I said a very important note. Speed depends mainly upon two factors. Am I right or not? One is nothing but elasticity. Another one is nothing but what? Inertia of the medium. Here elasticity. What is the thing elasticity here? It undergoes means that is nothing but tension. Due to the tension only, when you plug that, again it restores to its original position. Then what is the elasticity property in that? That is tension in the string. Tension in the string. And that string is having some mass. That is nothing but, that mass I am calling it. Inertia is nothing but linear mass density. What I am going to consider? Linear mass density. What is the elasticity property I have considered? Tension in the string. What is the inertia property I have considered? Linear mass density. That string will have some mass or not? And that is the inertia. That is the opposition offered. Linear mass density. We know that we have to write the dimension using dimensional analysis. Therefore, dimensional formula for this and for this. We know that tension has a dimension of, tension is denoted by T. Tension has a dimension of force. Tension is nothing but force. Force is nothing but what? According to Newton's second law, it is nothing but F is equals to ma and T is equals to. This is the formula for this. And for linear mass density, I am denoting it as mu. And it is defined as mass by length. It is one dimension, having only one dimension. That is mass by length. I can write it as m by L. This is the formula for this. Now let us write the dimensional formula for this and this. What I am going to write? Dimensional formula. For tension, T is equals to, mass is nothing but m kg is measured in m. Acceleration is L t to the power minus 2. You people would have learned how to write this in the second chapter. I am not going in detail. The mass is nothing but kg. Kg can be written as m. Acceleration is nothing but meter per second. Meter is length. Second is nothing but t. Meter per second square. I have written here. And here mu as a dimension. Mass is nothing but kg. That is nothing but L. Length is nothing but L. Is that clear? This is the dimensional formula. Let me call it as equation 1 and this is equation 2. Consider 1 divided by 2. What I am going to consider? 1 divided by 2. If I consider 1 divided by 2, then what happens? T by mu. What is the T I have written here? M L T to the power minus 2. What m mu I have written here? M into L. Am I right? Minus 1. It is in denominator minus 1. M gets cancelled. Denominator, I am taking it to the numerator. And L t to the power minus 1. If I take it to the numerator, it becomes plus 1. And L plus here 1, here 1. 1 plus 1 is 2. Is that clear? This is T by mu. Further simplification, here 2 is common. I am taking it out. And what happens? Whole square. L t to the power minus. This is T by mu. We know that velocity, call it as equation 3. We know that velocity is nothing but displacement by time taken. Displacement is nothing but measured in meter. Time is measured in second. What is the dimensional formula for this? Means it is V is equals to Dimension of meter is L. Dimension of time is t to the power minus 1. And velocity takes the dimension L t to the power minus 1. Substitute in 3. You substitute in 3, what you'll get? T by mu is equals to V whole square. Sending the square towards this side, then it changes to root T by mu is equals to V. This is the expression for what? For the velocity of a transverse wave on a stretched string. Very, very important note. What is the expression you have got here? V is equals to root T by mu. This is the expression for the velocity of a transverse wave on a stretched string. Once again I am repeating, we are not going to derive this by an analytical method. We are going to derive it by dimensional analysis. Here we are going to find out the speed. Speed always depends upon two quantities I said in the waves, elasticity and inertia. Under elasticity, what property here I am going to consider is tension. And under inertia, what property I am going to consider? Linear mass density. Tension as the dimension of force. Linear mass density is defined as mass by length. Force is nothing but ma, mass into acceleration. Mass is nothing but m, and a is nothing but lt to the power minus 2. Dimensional formula I have written for the for the tension. And for a linear mass density I have written it as mass by length, that is ml minus 1. Considering equation 1 by 2, 1 divided by 2, if I do, I will get in this fashion. Then it is lt to the power minus 1 the whole square. We know that velocity is equals to displacement by time, that is meter per second. The dimensional formula V is equals to lt to the power minus 1. Then substituting lt minus 1 can be written as what? V. Therefore in the place of this I have written V. Then it is V square. Sending square towards this side, then it becomes square root, it becomes t by mu. Then what is the speed of a transverse wave on a stretched string? Means V is equals to root t by m. From this I can say a very important note. Velocity is depends upon first one, tension in the string, and second it depends upon the linear mass density. It does not depend upon the frequency or wavelength, because it depends upon the source who is creating it. Keep a very note. Velocity depends only upon tension and linear mass density. It does not depend upon the frequency. Velocity does not depend upon frequency and wavelength. It depends upon source producing it. Source producing it. Is that clear? This is what about the speed of a transverse wave. See the expression for the speed of a longitudinal wave. Otherwise, it is nothing but speed of a sound. Let us find out the speed of the sound. Now I am speaking at what speed it is receiving in your hair. That is what we are going to see now. That is, sound is nothing but a longitudinal wave. Speed of a longitudinal wave, or otherwise speed of a sound. That is what we are going to determine now. Again, this one we are going to do by what method? Means we are not going to deal with analytical. We are going to deal with dimensional analysis. Using the dimensional analysis, let us derive this. Now before going to the content, let us understand the longitudinal wave. Here, see here, let us consider a wind pipe or flute or trumpet, anything you consider. In this it is having a air molecules. What it is having? A air molecules. On the other side you are having a piston. This is the piston. Through this piston you are going to push it or pull it. When you push it or pull it, this segment of air, this is nothing but I am considering the air to be in the form of segment. When you push this, what happens? All the air molecules which is present here will all gets to rush to this in this fashion. Again here it will start to rush to this point. Therefore a pattern is formed in which these molecules are moving in the direction of the propagation of a wave. Where you can find more molecules, that point I can say it as compression. Where you can find very less number of molecules, I can call it as rarefaction. In compression, what is the thing I would like to find out? Means density is more, pressure is more, volume is less. In rarefaction, what I can find? Density is less, pressure is less, volume is more. This is what I would have found out from this diagram. Therefore, compression, rarefaction, if it arises, then it is nothing but a longitudinal wave. Again, I said here velocity or speed depends upon two things. that is elasticity, and another one is nothing but inertia. Here what kind of elasticity it is undergoing means, see here, pressure is changing with respect to volume. If volume is less, pressure is more. If volume is more, then pressure is less. And what kind of elasticity it is arising with respect to pressure and volume means, it is nothing but bulk modulus. What it is nothing but bulk modulus, which you would have studied under mechanical properties of solids, chapter 9 of your first few physics. Bulk modulus, and it is denoted by the formula B is equals to delta P divided by delta V by V, where this P is called as change in pressure and this is called as delta V by V is called as fractional change in volume. Fractional change in volume. Is that clear? This is all about the bulk modulus, and this is the formula for the bulk modulus. Now coming to the next point, that is nothing but inertia. Under what property of inertia it undergoes means, see here, more number of molecules has been gathered here with respect to this volume. Therefore I am going to introduce a term called as mass density. What it is nothing but mass density, that is denoted by rho. What it is denoted by rho. Rho is defined as mass by volume. This is mass and this is by, this is the second parameter which is arising. Is that clear, students? Once again I am repeating here, we are going to find out the speed of a longitudinal wave. When you push this, what happens? More molecules get gathered at one point and less molecules on the other side. The more molecules where it gathers, I call it as compression, and less molecules I call it as rarefaction. In compression you can find density is more, pressure is more, volume is less. Vice versa of rarefaction. The density is less, pressure is less, and volume is more. We are going to derive under the dimensional analysis. Velocity depends upon two parameters. One is elasticity and another is inertia. Under elasticity, what type of elasticity it is means bulk modulus, because pressure is changing with respect to volume. Under inertia, what type of inertia means mass by volume. More molecules are crowded with respect to this area volume it has occupied, that is mass by volume. Now I have to write the dimensional formula for this too. The dimensional formula I am going to write, which you have learned already. I am not going in detail for it. Bulk modulus dimensional formula I am going to write. This is nothing but Pascal. SI unit of bulk modulus is nothing but, yes, here volume gets cancelled, only it is pressure. Pressure is force per unit area. This dimensional formula is given by ml minus 1 t to the power minus 2. Is that clear? This is the dimensional formula for what? Bulk modulus. Calling it as equation 1. Similarly, here I am writing the mass is nothing but m, volume is nothing but L cube. This is equation 2. Same what I did in the previous derivation, same I am doing here. Very important, writing the dimensional formula. How to write the dimensional formula I said here. Volume gets cancelled, then pressure. SI unit of pressure is Pascal. Pascal is nothing but force per unit area. That force is nothing but by area. If you do, you will get this, and here mass by volume. If you do, you will get this. Equation 1, equation 2. Consider 1 divided by 2, then B divided by rho becomes ml minus 1 t to the power minus 2 divided by ml to the power minus 3. Gets cancelled, minus 3 taking it to the numerator. B by rho is L minus 1 t to the power minus 2 t minus 1 minus 3 goes to the numerator, becomes plus 3. See here, L minus 1, L plus, and L 3 minus 1 t to the power minus 2. Then L2 t to the power minus. This is your B by rho. Taking 2 as common, then Lt minus 1. I take, then it is B by rho. I know that Lt minus 1 is the dimensional formula for velocity, that is speed or velocity. Then B by rho is equals to V square. Sending square towards this side, and B by rho is equals to V. From this I can say that the speed of the sound in air medium. This is for what medium? Here I have considered air. Flute or trumpet means what is present? Air. This is for air medium. Speed of sound in which medium? For air medium. Speed of sound in air medium is given by V is equals to square root of B by rho, where B is called as bulk modulus. Suppose it is a solid medium, then what happens? Bulk modulus will change to what? Young's modulus. Am I right or not? For air medium it is bulk, for solid it is nothing but Young's modulus. This is the very important note I am bringing forward. Here air if you consider, then it becomes B. If you consider through a material, that is railway track, in the track if you keep your ear and if you listen, you can hear the vibrations of the sound coming. Then here the sound is propagating through the solid, that is nothing but your Y, Young's modulus. Very very important note I am bringing forward. Listen carefully. Note. What is the note means? Young's modulus is very much greater than the bulk modulus. Here I can say that velocity is directly proportional to the modulus of elasticity. See here, V is proportional to Y and V is proportional to B. That means modulus of elasticity. We know that Y is greater than B, that is modulus of elasticity. Then velocity of sound in solids is greater than velocity of sounds in gas. This is very 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 important. Sound travels faster in which medium? Solids than in the air medium. Is that clear? Very very important note I have given here. Velocity of sound is more in solids than in the gas. According to the ascending order I have to write means velocity of sound is greater than velocity of sound in liquid, and that is greater than gas. This is how it goes. Understood? So far we have discussed about the speed of a longitudinal wave, that is speed of a sound. That formula is given by V is equals to square root of B by rho. It is given by what? V is equals to B by rho, and Y by rho is nothing but for solid, and this is for air. And here it is goes like this. Velocity of sound in solid, it is very much greater than velocity of sound in gas. According to the order if you write means in solid it is very very high than in the liquid, then liquid is greater than gas. Is that clear? This is all about the speed of a longitudinal wave. Now how to find out the exact value I will tell you now. Now we are going to see about the speed of a sound in air by Newton. Otherwise it is also called as Newton's formula. What it is called as? Newton's formula. So far we are discussing about the speed of the sound in air. What is the expression you have got for speed of the sound in air? Means speed of sound in air, that is V is equals to square root of B by rho. Let me call it as equation 1. Speed of sound in air by Newton. Now Newton is going to give the explanation to calculate its value. That is also called as Newton's formula. Just now we know that speed of sound in air, just now we have derived this. V is equals to square root of B by rho, where B is called as bulk modulus, rho is called as mass density. What it is called as? Mass density. What Newton is arguing means, or what Newton is considering means, this is Newton's assumptions. Newton's assumption. Here this is a wind column. In this wind column it is having a segments of air. Just now I explained this is compression and this is rarefaction compression. Here it is nothing but molecules. Here more molecules are crowded, less molecules, more molecules are crowded. And this is the direction of propagation of sound. Here you can see at compression pressure is more, and at rarefaction the pressure is less pressure. There is a variation of pressure. Variation of pressure in the medium. Understand clearly. Variation. What is variation? That pressure. Variation of pressure in medium during propagation of, this is during propagation of sound. There is a constant temperature. There is a constant temperature between compression and rarefaction. Between compression and rarefaction, what happens? Variation of pressure in the medium during propagation of sound is there is a constant temperature. Temperature remains, what he is saying, constant between the compression and rarefaction. This is what Newton is assumption. Then if temperature is constant, what is here? If temperature is constant, then it is called as isothermal process. What it is called as? Isothermal process. Once again I am repeating here. Your temperature remains constant between the compression and rarefaction. If temperature is constant between compression and rarefaction means, then I can say it is an what kind of process means it is an isothermal process. In an isothermal process, what is constant? Temperature is constant. Yes. Now again going back to the ideal gas equations for isothermal process. For isothermal process, the ideal gas equation is given by PV is equals to constant. This is the ideal gas equation, calling it as equation 2. For what kind of process it is? Isothermal process. Newton assumption is nothing but it is an isothermal process. Very, very important. We consider the compression and rarefaction between them, temperature remains constant. Then it is what kind of process? Isothermal process. For isothermal process, ideal gas equation is given by PV is equals to constant. See the figure here. Pressure is less, pressure is more. Volume is more, volume is more. Here volume is less. Therefore, there is a change in pressure and volume. Therefore, differentiating equation 2 becomes, here pressure also changing, pressure and volume both changes. What this both are changes. Then what happens? P delta into PV is equals to delta into constant. And what happens here? This constant becomes 0. Differentiation of constant is 0. Here it is product form, that is U into V, delta P into V plus P into delta V. UV form I have used and I have done delta into P first into V plus P into delta V I have multiplied. Sending this term towards this side, this term I am sending to that side. Then what happens here? P delta V is equals to, if it goes to that side it becomes minus delta P into V. Then P is equals to minus delta P. Delta V is sent to that side, then it goes to this V can be written as 1 divided by 1 by V. Therefore, I am rewriting it. Then it becomes 1 into 1 divided by V. This V I have written in this fashion. Denominator of denominator again goes to the numerator. It becomes to the normal form. Delta V by V. Therefore, this is nothing but, we know that delta P by delta V by V is equals to B. Substitute in 3. This is equation 3. If I substitute in 3, what I will get there? P is equals to B. Then that pressure is equals to what? Bulk modulus. Substitute in equation 1. I'm going to substitute in equation 1. I know that V is equals to what it is? Root. In the place of B, now I have to write what? P by rho. This is the expression for speed of sound in air. By whom? By Newton. This is called as Newton's formula. Now what Newton is going to do means, at normal temperature and pressure, what is the value of pressure he found means 1.01 into 10 to the power of 5 Pascal, and the density of air, rho is nothing but density of air, that is for air it is 1.29 kg per meter cube. On substituting this in this, V is equals to square root of 0.1 into 10 to the power of 5 divided by 1.29. We got it as 280 meter per second. This is according to whom? According to Newton. But experimentally they did and got the value of sound. Experimental value was found to be 332 meter per second. This is the experimental value, but according to Newton he has got how much? 280, and experimental value is 332. What Newton has did is wrong. There is a small correction in Newton's assumption. This is all about the Newton's formula. Once again I am repeating, speed of sound in air was found to be V is equals to B divided by rho, and then I considered Newton's assumption. According to Newton's assumption, what is the assumption made by the Newton means? He considered it to be an isothermal process. What it is? An isothermal process. That is, between compression and rarefaction, during the propagation of the sound, there is constant temperature between C and R. If temperature is constant, then it is called as an isothermal process. That is what I depicted here. And then for isothermal process, the ideal gas equation is given by PV is equals to constant. From figure I can see that pressure and volume are changing, both changes. Then differentiating with respect to that, therefore delta into P is delta P into V plus P into delta V. UV form I have done is equals to, change in constant is what? 0. P into delta V, send this full term towards that side, where V can be written as 1 divided by 1 by V, denominator of denominator goes to numerator, P is equals to, we know that bulk modulus formula is this, substituting this over here, and I will get P is equals to, this full thing I can write it as what? B, I have written here, and V is equals to square root of P by rho. This is called as Newton's formula. At normal temperature pressure, what is the pressure here? 1.013, density is 1. On substituting in this formula, we got the value to be 280 meter per second. But experimentally they did and found the speed of sound to be 332 meter per second. But what here it is 280. According to this Newton's assumption, this is wrong. Now another person is coming forward to correct the Newton's formula by name called as Laplace. That is what we are going to see now. Now we are going to see again the speed of sound in air by Laplace method. This is also called as Laplace correction to the Newton's formula. That Newton was wrong, am I right or not? Newton's formula. What does the Newton's formula says? The Newton formula, just now we have derived that Newton's formula for velocity, it is P by rho, pressure and volume. Using this he found the value to be 280 meter per second, but absolute value is 332 meter per second. That is the exact answer for the speed of the sound, that is 332. But what Newton has got there, he has got it as 280, therefore which is wrong. Now let us see what Laplace is going to do to correct that. Now again coming to the diagram, here it is compression, rarefaction. Here, see here, according to Newton considered it is what kind of process? Isothermal process. What it is? An isothermal process. All this was said by whom? All this was said by Newton. Now we are what Laplace is going to do. Let us understand here. This is Laplace assumption. Laplace is pointing out that the variation in pressure, what he says, here pressure is varying, here it is less pressure, here it is more pressure. He is pointing out the variation of pressure in the medium during the propagation of the sound is very fast itself, but it is very fast. That means there is a little time, it is very fast, that sound propagation, there is very little time between the rarefaction and compression. There is a very small time between these two for the heat to flow. For what? Heat to flow, so that to maintain the temperature as constant. According to Laplace assumption, he says that the variation of pressure, understand this, the variation of pressure in the medium during propagation of sound is so fast, that is a little time is required for heat to flow between compression and rarefaction to maintain constant temperature. This was said by whom? Laplace. Very important point I am drawing here. This also said by whom? Newton. Variation of pressure in the medium during propagation of sound. Temperature remains constant. This was said by whom? Newton. But this extra thing is added by whom? Means by the Laplace. So fast that there is a little time is required for the heat to flow. There is a need of heat to flow between compression and rarefaction to maintain what? Constant temperature. Therefore, it is not an isothermal process. It is not an isothermal process. Before that it undergoes, it is not an isothermal, it's an adiabatic. It's an what? Adiabatic process. It's an adiabatic process. This is what pointed out by Laplace. Newton says it is an what process? Isothermal. But Laplace says it is an adiabatic process. What it is? An adiabatic process. Now let us see according to Laplace. Ideal gas equation. We know that ideal gas equation for an adiabatic process. What is the ideal gas equation for an adiabatic process? Means that is PV is equals to constant. This is for what? Newton. Now for isothermal, here gamma, this indicates is nothing but, this is nothing but the specific heat ratio. What it is? Nothing but specific heat ratio. Calling it as equation 1. What I am calling it as equation 1. Yes, here differentiating. What I am going to do? Differentiating equation 1. P and V changes. Pressure and volume are changes. And what happens here? Delta of P V to nu is equals to delta of constant. Differentiating. Now differentiation of a constant is 0. First delta into P. Delta P V of gamma over first UV form. UV over U over. Now I have to differentiate the V. P remains constant. Differentiation of x to the power n is nu into x to the power n into differentiation of this is equal to 0. This is the formula which I have brought forward. Differentiation of x to the power n is n into x to the power n minus 1 into delta x. Like that I have used and I have done. Go and refer the previous class of mine, that is in motion in a straight line. There I would have done this. Now coming back to this full term I am sending to that side, then it becomes P nu. Nu to the power gamma minus 1 can be written as gamma minus 1 into delta V is equals to this full term I am sending to that side, then delta P V to the power gamma. Plus if it goes that side it becomes minus. Is that clear? V to the power gamma gets cancelled. Now P nu V to the power minus 1 can be written as what? 1 by V to delta V is equals to minus 10. Send all the terms to the other side. Then what happens here? P is equals to minus delta P. This one goes to the denominator. This one goes to the numerator. And this one goes to the denominator. In P is this what I said you to write, delta P whole denominator of denominator goes back to the numerator, 1 by rho into, calling it as equation 2. Is that clear? Now coming to the point, we know that bulk modulus B is denoted as minus delta P by delta V by V. Substitute in 2. Then what happens? P is equals to B by rho. Am I right? Sending this rho towards this side. Then P into rho is equals to, sorry, it's gamma. P into gamma. It's gamma. P into gamma is equals to B. This gamma, 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 as it remains. Therefore call it as equation 3. Therefore, according to Newton it was B is equals to P, but according to Laplace it is B is equals to P into gamma. We know that V is equals to square root of B by rho. Substitute 3 in above. Then what happens? Square root of, in the place of B I can write P into gamma divided by rho. This is the formula by Laplace or Newton's correction. Newton's formula. Correction to the Newton's formula. This. Now at normal temperature pressure, P is equals to 1.01 into 10 to the power of 5. Rho is equals to 1.29 kg per meter cube, and this is Pascal, and gamma value it is 7 by 5, that is 1.4 for dry air. This is specific heat ratio. Once you substitute all this value in the above equation, you will get it as 331.4 you will get, that is approximately equal to 332 meter per second. This is the value which was got by Laplace. Experimental value also it is 332. Here by using his formula he got it as 331.4. he has got that, approximately we can write it as 332 meter per second. Therefore this is all about the Laplace correction. Once again I am repeating, listen carefully. According to Newton he considered it to be an isothermal process, but Laplace is pointing out it to be an adiabatic process. Why it is an adiabatic process means the propagation takes so fast, that means the little time is required for the heat to flow, because compression and rarefaction to maintain constant temperature. Between compression and rarefaction to maintain constant temperature, heat has to flow. It is an isothermal process. It is not an isothermal process, it's an adiabatic process. Ideal gas equation for adiabatic process I have written here. Differentiating equation 1, where P and V is changing. If I differentiate, I get it as UV form. I have differentiated delta P into V to the power gamma, plus P remains as it is. Now V I have to differentiate. Gamma V gamma minus 1 into delta V. This is of the form x to the power n. X to the power n is nothing but n into x to the power n minus 1 into delta x. That form I have used and I have done. And then V to the power gamma minus 1 can be written as V to the power gamma, V to the power gamma minus 1, gamma gets cancelled, V to the power gamma. Then after simplification I get this form. Again I know by definition B is equals to, the substituting that I'll get it as this form. We know that V is equals to root B by P. Then in the place of B I can write it as P gamma by rho. This is the Laplace formula or correction to the Newton's formula. Only P by rho was there. Additional to that gamma has been added. By doing this I will get it as V is equals to 331.4 meter per second. Experimental value is 332, which is approximately equal to that. Therefore this is the expression for the speed of the sound in air. When you speak, at what speed it reaches to the receiver means it reaches at this speed, that is 332 meter per second. This is the speed of the sound in the air. Is that clear, students? Thank you, students.